In the depths of the Leo constellation, positioned 120 light-years distant from our pale blue dot, an astronomical instrument has captured evidence that will fundamentally transform our understanding of life's place in the cosmos. The James Webb Space Telescope has identified a distant world where atmospheric temperatures remain constant at precisely 49 degrees Celsius, that's 120 degrees Fahrenheit for those of us measuring in the old way, enveloped within an atmosphere that resonates with the unmistakable chemical fingerprints of biological activity. The scientific community stands at 99.7% certainty. They've discovered it. A planet absolutely saturated with life, potentially even more conducive to biological systems than our own Earth. If this captures your imagination, hit that subscribe button and join us as we decode the electromagnetic whispers and cosmic narratives etched across the celestial sphere. The data packets materialized on a Tuesday morning in December, concealed within cascading streams of electromagnetic radiation captured by the James Webb Observatory. Inside his office at Cambridge University, astrophysicist Niku Medusan found himself transfixed by his computer display, observing the subtle fluctuations and variations in luminosity that had traversed more than a full century through the emptiness of interstellar void. Each undulation represented a puzzle piece, a cryptic tale encoded within subatomic particles of light. Then the irregularity appeared, a solitary molecular compound that had absolutely no business being present in that spectral analysis: dimethyl sulfide. Here on our home planet, this particular molecule emerges exclusively from living processes, from microscopic plankton drifting through oceanic currents, from bacterial colonies thriving in terrestrial soil, from the metabolic processes of innumerable invisible microorganisms. It doesn't spontaneously form from volcanic eruptions or atmospheric electrical discharges or geological mineral interactions. Only biological systems manufacture it. Only life creates this specific chemical signature. The electromagnetic signal wasn't subtle or questionable. The mathematical probability of measurement error stood at less than 3 in 1,000. Medusan's hands experienced involuntary tremors of excitement and anticipation. Somewhere across the impossible distance of 120 light-years, something alive was broadcasting its existence into the vacuum of the cosmos. The world that generated this signal bears the designation Keitetsu de 18b, and it maintains an orbital path around a diminutive red dwarf star within the Leo constellation. This celestial body possesses approximately 8 times the mass of Earth, substantial enough to retain a deep, layered atmosphere, yet compact enough to avoid collapsing into a gaseous giant like Jupiter or Saturn. For many years, astronomers operated under the assumption that such worlds were fundamentally too hostile for biological development. Their dense hydrogen envelopes, their crushing gravitational forces, the entire environmental package appeared utterly unwelcoming to the delicate chemistry of life. Webb's comprehensive data told a radically different story. Beneath that substantial atmospheric blanket, temperatures stabilize around 49 degrees Celsius, or 120 degrees Fahrenheit. Warm, certainly, but sufficiently gentle to permit liquid water, that universal solvent so crucial to biochemistry as we understand it. The hydrogen layer functions as an ideal thermal insulator, capturing heat energy and redistributing it uniformly across the planetary surface, creating conditions of remarkable stability. Medusan's research team had dedicated months to studying this distant world, capturing the infinitesimal starlight that filtered through its atmospheric layers each time the planet transited across the face of its parent star. Each astronomical transit unveiled additional revelations. Initially, they detected water vapor. Then methane appeared in the spectroscopic data. Carbon dioxide followed. This cocktail of atmospheric gases collectively painted a portrait of equilibrium and stabilization. And finally, the definitive discovery: dimethyl sulfide, the unambiguous molecular signature of biological activity. In the discipline of astronomy, absolute certainty remains an elusive commodity. Most astronomical discoveries begin as tentative whispers of possibility, theories easily overturned or revised by subsequent observational data. But this particular finding carried a statistical confidence level of 99.7%, a degree of mathematical certainty typically reserved for the detection of fundamental subatomic particles or the observation of gravitational wave phenomena. For the first time in human history, we weren't merely speculating or theorizing. We possessed genuine statistical confidence. We were almost completely certain. The planet's substantial atmospheric envelope operates like a planetary-scale greenhouse system, but crucially, not a destructive one. Rather than trapping heat to catastrophic levels, it establishes thermal equilibrium across the entire world. Water neither crystallizes into ice nor vaporizes into steam. It simply persists, vast, profound, and remarkably stable. Such a planetary environment would represent paradise for complex chemistry. Life would face no necessity to struggle against seasonal droughts or frozen winters. Evolution could proceed continuously, uninterrupted, like an eternal symphony that never reaches its final note. The parent star burns with far less intensity compared to our own sun. Small, remarkably steady, and possessing near immortal longevity. Red dwarf stars persist for trillions of years. Not billions, but trillions. Their fusion reactions proceed slowly, but eternally. Around such stellar objects, temporal duration itself becomes extraordinarily generous. Any initial spark of biological chemistry that ignites within their habitable zones might possess ages beyond human comprehension to develop, adapt, and fundamentally transform. When the preliminary results received public announcement, the entire scientific community experienced a collective pause. For decades, we'd been searching specifically for Earth's astronomical twin, a rocky planet maintaining an orbital path around a yellow star similar to our Sun. Yet here existed something completely different, and somehow even more optimally suited to supporting biological systems. It wasn't attempting to replicate Earth. It represented an entirely new category of habitable planetary environment. Vast oceans stretching beneath alien skies. Life sustained not through resemblance to terrestrial conditions, but through the universe's own innovative creativity. To observe such a distant world, Webb had to perform what can only be described as technological miracles. Suspended approximately 1 million miles from Earth at a gravitational equilibrium point designated L2, the telescope exists in perpetual darkness. Its 5-layer sun shield, roughly the size of a professional tennis court, maintains instrumentation at temperatures colder than the frozen surface of distant Pluto. 18 golden hexagonal mirrors, each representing a masterpiece of geometric precision, collect electromagnetic radiation invisible to human eyes. Collectively, they create a reflective surface so extraordinarily precise it could theoretically detect the thermal signature of a bumblebee resting on the lunar surface. When that distant planet drifts across the face of its star from our observational perspective, a minuscule fraction of stellar light filters through its atmospheric layers. Molecular compounds within that atmospheric envelope absorb specific electromagnetic wavelengths, leaving subtle imprints, a spectral fingerprint unique to that world's chemical composition. By decoding those intricate patterns, Webb reveals the planet's atmospheric chemistry. It's analogous to identifying an individual person by analyzing the molecular composition of their breath. But detecting that infinitesimal whisper across such impossible distances presents unimaginable technical challenges. The host star radiates billions of times more brilliantly than its orbiting planet. To overcome this overwhelming disparity, Webb employs its coronagraph, a sophisticated masking device that blocks the star's blinding glare, functioning like strategically positioning your thumb to block the sun and observe a firefly nearby. The remaining filtered starlight undergoes analysis and noise reduction through algorithms so mathematically precise they can isolate a handful of meaningful photons from millions of meaningless ones. Those precious photons carry narratives older than living memory. Each individual particle of light departed its home world 120 years ago, around the historical period when humans first learned to transmit radio wave communications into the sky. Now, a full century later, it conveys the message that life was already flourishing elsewhere in the cosmos. It's profoundly humbling to realize we're not discovering life as it begins its first tentative steps, but as it existed a century ago, an aged echo of a living planet that has very likely continued thriving ever since. The atmospheric composition revealed considerably more than simple chemistry. It revealed active behavior. Methane, carbon dioxide, and water vapor formed a delicate balance, a kind of planetary metabolism. On a completely lifeless world, Such gaseous compounds would react quickly and settle into chemical equilibrium. But equilibrium wasn't what Webb's instruments observed. Instead, the molecular ratios fluctuated continuously, a chemical disequilibrium. The identical signature that defines Earth's biologically active atmosphere. Life doesn't permit static balance. It constantly reshapes and redefines its environment. Breathing, consuming, exhaling, recycling. Even the planet's conspicuously absent gases told their own compelling story. If K2-18b were genuinely lifeless, its atmospheric composition would contain significant quantities of ammonia. But ammonia appeared almost entirely absent from the spectral analysis, as though something were actively utilizing it, converting it into other compounds, essentially cleaning the atmospheric composition. On Earth, microbial organisms perform exactly that function. The deeper the analytical investigation proceeded, the clearer the overall picture became. Not a sterile, dead world, but a thriving one. Not a random fluke of chemistry, but an ecosystem operating at planetary scale. Statistically speaking, the confidence level proved overwhelming. A 3 sigma detection representing 99.7% certainty, meaning the mathematical chance of measurement error stood at roughly 1 in 1,000. In any other scientific field, that constitutes proof beyond reasonable question. And yet, no statistical number could adequately capture the philosophical enormity of what it implied. For countless centuries, humanity had posed the fundamental question of whether life existed elsewhere in the universe. Now, for the first time in our species' history, the answer wasn't based on speculation or philosophical debate. It was based on measurement, on observable, quantifiable data. To reach that momentous conclusion, Webb had to detect molecular patterns measuring only a few parts per billion in concentration, the spectral equivalent of hearing a single heartbeat through the chaos of a hurricane. Light wavelengths were measured to precision levels of 1 part in 10 million. Each electromagnetic wavelength meticulously recorded and compared, every alternative explanation systematically ruled out through rigorous analysis. Contamination from Earth? Impossible. Random instrumental noise? Statistically negligible. The simplest explanation, indeed, the only scientifically viable explanation, was biological activity. That's precisely why, the moment the data received confirmation, every scientist who examined it experienced the same profound emotional weight. This wasn't merely another exoplanet discovery. This was the end of cosmic solitude for humanity. The planet's vast oceans, extending potentially hundreds of miles in depth, blur the traditional distinction between sea and sky. The water mixes intimately with hydrogen, creating a liquid medium that maintains stability across a staggering range of temperatures and pressures. Such exotic chemistry could nurture life forms beyond our wildest imagination. Organisms that respire hydrogen instead of oxygen, deriving energy from methane instead of photosynthetic sunlight. Under its perpetual cloud cover, atmospheric pressure builds into conditions we can barely simulate in terrestrial laboratories. Diamonds may crystallize and precipitate through the atmosphere like rain, glittering downward into the oceans like frozen stars. Somewhere below that luminous haze, in the warm twilight waters, life is almost certainly stirring. Not fragile, not temporary, but ancient beyond measure and abundant beyond counting. This realization fundamentally changes everything we thought we understood. If biological systems can thrive in hydrogen-rich seas orbiting a red dwarf star, then life isn't a cosmic rarity. It's an inevitable outcome of physics and chemistry given sufficient time. 3/4 of all stars in our Milky Way galaxy are red dwarfs, quiet, enduring suns with planetary systems just like this one. If even a modest fraction host active biospheres, then our galaxy is absolutely overflowing with living worlds. The discovery redefines what the term habitable actually means. It demonstrates conclusively that life doesn't require an Earth clone or Earth-like conditions. It only requires balance, the appropriate chemistry, the appropriate temperature range, and the appropriate patience across geological timescales. Webb's golden mirrors accomplished more than passive observation. They connected us to another chapter of cosmic creation. Each photon it captured carried a whisper across space and time, the breath of an unseen ocean, the metabolic sigh of life beyond our physical reach. In that faint electromagnetic radiation, humanity found conclusive proof that existence is shared across the cosmos. that we are not the first intelligent species to wonder about the universe, not the only biological systems in existence, and certainly not the last to emerge. The universe, it appears, has been alive for more time than we can logically comprehend or easily imagine. The red dwarf at the gravitational heart of this planetary system measures small enough to fit comfortably inside Jupiter, yet possesses sufficient density to hold a planet like K2-18b in its gravitational embrace for eternity. Its luminosity appears dim to our perception, a deep ember red rather than the fierce white radiance of our sun. To human eyes, it wouldn't blaze brilliantly across the sky. It would glow, soft, constant, patient, eternal. This is not a star that lives fast and dies young in cosmic terms. It burns slowly, almost tenderly, stretching its functional lifetime, not into mere billions of years, but into trillions. On the cosmic scale of stellar evolution, it is nearly immortal. That extraordinary longevity changes everything about planetary habitability. Around our sun, luminosity shifts over time. Planetary climates wobble and fluctuate, and mass extinction follows mass extinction. But here, around this red dwarf, the light remains steady and unchanging. The same warmth persists century after century, millennium after millennium, eon after eon. No wild stellar flares to strip away protective atmospheres. No chaotic variations to undo the patient work of chemistry. For a world like K2-18b, that stellar constancy means something truly extraordinary. Oceans that never freeze solid, clouds that never vanish completely, and time, endless, generous time for life to emerge, adapt, and endure without major interruptions. For decades, scientists dismissed red dwarf stars as fundamentally unfit for supporting life. They are small, cool, and their habitable zones lie so close to the star that any planet must orbit almost intimately close, nearly hugging the stellar surface. But what once appeared dangerous now reveals itself as ideal for biology. K2-18b completes a full orbital year in just 33 Earth days, close enough to receive the warmth of its dim sun, yet sufficiently distant to remain calm and stable. One hemisphere perpetually faces daylight, the other sleeps in endless darkness. From space, it would resemble a glowing marble, half bathed in crimson light, half wrapped in shadow. Yet even that night side is not frozen or cold. The planet's thick hydrogen atmosphere acts as a vast planetary conveyor system of heat, moving thermal energy across its skies through atmospheric circulation. That stability is extraordinarily rare in the universe. It gives water permanence across the surface, allows weather patterns to flow without catastrophic violence, and provides chemistry with the peace and stability necessary for complexity to emerge. If life exists there, it evolves beneath the sun that never rises above the horizon, never sets below it. A world perpetually caught between dawn and dusk, where the boundary dividing day from night is not a frontier to cross, but a stable habitat zone to inhabit. Under that eternal twilight, the color of the sky would never be blue like Earth's. It would burn in layered hues of crimson, violet, and copper, dim but endless and unchanging. The star would hang motionless above the horizon, fixed in the same celestial position forever. The oceans below would reflect that red light, glowing faintly as waves move under a horizon perpetually blurred by atmospheric haze. On the night side, darkness would not be absolute or complete. The dense atmospheric composition would scatter the star's glow around the planetary curvature, painting the blackness in faint metallic hues. Even there, in perpetual shadow, light would linger. The glow of auroras dancing in the upper atmosphere, the shimmer of lightning inside distant cloud formations. This is not a planet of sharp contrast, but of gentle gradients, one where everything shifts smoothly and gradually, never abruptly or violently. If evolutionary processes began here, they did so with extraordinary patience. On Earth, life was fundamentally shaped by disaster, asteroid impacts, ice ages, volcanic cataclysms, and sudden bursts of fire. But around this quiet sun, there are no mass extinctions, no sudden ends to evolutionary lineages. The rhythm of time proceeds slower, the canvas broader and more generous. Life here could grow ancient without major interruption, carried forward on the calm breath of a red dwarf dawn that never truly changes. Webb's sophisticated instruments were specifically designed to see in this kind of electromagnetic radiation. Infrared, the very wavelength red dwarfs emit most strongly and abundantly. That is precisely what made K2-18b's spectral signature so remarkably clear and definitive. The telescope wasn't straining to detect something faint or marginal. It was tuned to the exact electromagnetic language of the star itself. Every beam of infrared radiation carried within it the encoded information of the planet's atmospheric composition, the thermal signature of clouds, the molecular scent of oceans, the breath of unseen organisms. Each time the planet crossed the face of its star from our observational perspective, a minuscule fraction of starlight slipped through its atmospheric envelope. Molecules absorbed that light at precise, specific wavelengths, leaving faint spectral notches, fingerprints unique to each chemical compound. Webb read them like a cosmic diary written in electromagnetic radiation. The pages spoke clearly of water, methane, carbon dioxide, and finally dimethyl sulfide, the unmistakable mark of biological activity. To human eyes, the red dwarf would appear unremarkable, barely visible in Earth's night sky even with optical aid. Yet that very dimness makes astronomical discovery possible. The smaller the star, the easier it becomes to detect and characterize its planets. The overwhelming glare is reduced. The spectral signals are cleaner and more distinct. What seems weak is in truth perfect for observation. Red dwarfs are not obstacles to planetary detection. They are cosmic magnifying glasses, revealing the faint whispers of their worlds with unprecedented clarity. If we could somehow stand on one of K2-18b's high plateaus and look upward toward the sky, the view would be surreal and alien. The horizon would curve beneath a bronze-tinted sky. The air would shimmer with heat and humidity. The sunlight would feel soft, more like pervasive warmth than intense brightness. Shadows would be long and lazy, stretching forever across the landscape. The concept of day and night as we understand them would fade and dissolve, replaced by slow shifts in atmospheric tone, in temperature, in the very heartbeat of the planet itself. Life, if it exists there, would move differently than terrestrial life. Plants might be dark in color, black, deep indigo, or dark violet, absorbing every stray photon of red light for photosynthetic energy. Photosynthesis would be slow but steady, a patient accumulation rather than rapid growth. The creatures that graze on them might sense their environment through vibration or pressure differentials rather than visual sight. Nothing would hurry on such a world. Energy is scarce compared to Earth, but time is infinite. Evolution would naturally reward patience over speed, endurance over aggression, stability over rapid change. The red dwarf's greatest gift to its planets is moderation. It burns with discipline, never wasting energy, never surging unexpectedly. While our sun will expand into a red giant and eventually die within 5 billion years, K2-18b's parent star will still be glowing softly when the Milky Way galaxy has evolved and changed beyond recognition. For the life orbiting it, apocalypse is a word without meaning or context. When Webb's instruments detected and analyzed light from K2-18b, that electromagnetic radiation had been traveling through space for 120 years. When it began its journey, the year on Earth was 1905. Einstein was writing his revolutionary papers about relativity. The Wright brothers were testing powered flight. Our species had barely learned to reach the sky, while that distant planet had already been breathing beneath crimson clouds for eons. It means that what we observe is not the present, but the past. A frozen memory of a living world as it existed a full century ago. And when we look again, decades from now, with even more sophisticated instruments, we will still be catching up to that distant moment. Astronomy is always a conversation across vast stretches of time, and the universe speaks slowly, patiently. Yet even a whisper from 120 light years away can fundamentally rewrite everything we believe about existence. The chemistry in that distant atmosphere, the mixture of gases, the chemical imbalance that only active biology can maintain, it all dances to the steady beat of its star. The red dwarf provides a constant rhythm. The planet answers with metabolism and change. Together they form a perfect loop, one stable, one alive. It is a relationship of opposites, a cosmic duet between fire and breath. The star gives constancy and reliability. The planet gives change and adaptation. One burns eternally, the other renews continuously. Our own world began in chaos, fire and impact, the violence of a young planetary system. But around a quiet red dwarf, life could begin in peace and stability. The glow is faint compared to our sun, but for a planet like K2-18b, it is absolutely sufficient. Enough warmth for liquid oceans, enough light for complex chemistry, enough time for everything to unfold. Perhaps that is the universe's quiet truth that we're only now beginning to understand. That life does not crave brilliance or intensity, only balance. That biological systems can bloom under crimson skies as easily as under blue. That existence itself is adaptable, universal, and patient beyond measure. So when we look towards the constellation Leo and see that faint red spark in our telescopes, we are not seeing emptiness or sterile void. We are seeing endurance. A sun that has been burning softly for billions of years and will continue burning for trillions more. And beneath its calm glow, behind curtains of hydrogen and atmospheric mist, a living world may still be turning slowly, silently, in the light of an immortal star. The light from K2-18b's red sun filters through multiple layers of hydrogen and water vapor before it reaches the oceans far below. To the human eye, those skies would not be blue like Earth's, but pale amber, shading to deep rose near the curved horizon. Clouds drift slowly, broad and dense, tinted by the faint copper glow of the star. The air itself would shimmer visibly, heavy, rich, almost luminous, a living lens of gas that both shields and sustains whatever exists beneath. This atmosphere is the planet's great architect and engineer. It is not thin and fragile like Earth's atmospheric envelope, but vast and thick, extending hundreds of kilometers deep into space. Hydrogen dominates the composition, laced with carbon dioxide, methane, and water vapor. Together, they create a powerful greenhouse effect, yet not a destructive or runaway one. Instead of scorching the surface to sterility, the heat spreads evenly, keeping the world in thermal equilibrium. Water neither freezes solid nor boils away. It simply endures, flowing through endless cycles of vapor and rain. From orbital perspective, the upper atmospheric layers appear calm and serene, but deeper down, the air grows dense enough to blur the traditional line between sky and sea. The clouds merge seamlessly with mist. Mist dissolves gradually into ocean. The boundary of air and water is not a sharp surface, but a gradient, a slow, imperceptible fading of one state of matter into the other. Beneath that soft veil of atmosphere, sunlight weakens progressively, replaced by a crimson glow that seeps through like light filtering through stained glass windows. The ocean itself may extend hundreds of kilometers deep, far beyond any pressure our current submersibles could survive. Hydrogen mixes freely with water molecules, creating a liquid unlike any found on Earth. Lighter, more compressible, able to remain fluid across an enormous range of temperatures and pressures. It is a sea where chemistry reigns supreme, a cradle of molecules that might assemble, divide, and ultimately breathe. If life exists there, it likely began in those unfathomable depths, far from the reach of light. On Earth, we once thought sunlight was absolutely essential to the origin of life. But at the bottom of our own oceans, near volcanic vents, we found entire ecosystems that thrive in complete darkness, powered not by solar radiation, but by chemistry. They live on geothermal heat and dissolved minerals, on gradients of energy, rather than rays from the sun. The same principle could be true on K2-18b. Its oceans may harbor hydrothermal fields where hydrogen and carbon mingle continuously, giving rise to the first spark of biological chemistry. The pressures down there would crush terrestrial steel like paper. Yet for living cells, pressure can be protection rather than threat. It stabilizes fragile molecules, drives chemical reactions forward, and keeps water liquid even when temperatures soar. If microbes ever took hold in those depths billions of years ago, evolution would have had countless calm, stable years to perfect them, to refine their chemistry, to expand their capabilities. Webb's instruments obviously can't see that far below the cloud layers, but the atmospheric composition above betrays what happens beneath. The gases we detect, methane, carbon dioxide, traces of dimethyl sulfide, suggest an active cycle connecting sea and sky in continuous exchange. On Earth, that balance is maintained by life in all its forms. Algae producing methane, microbes consuming it, plants exhaling oxygen. On K2-18b, something similar could be at work. though shaped by very different environmental rules and constraints. The absence of ammonia is another crucial clue. On dead, geologically inactive planets, ammonia tends to build up over time, a leftover product of chemical decay. But here it's conspicuously missing, likely converted into more complex organic compounds or broken apart by living metabolism. Even without seeing a single organism directly, the atmosphere behaves as if it is being constantly adjusted, tuned, and renewed by biological processes. Imagine standing, or perhaps floating, somewhere within that exotic environment. The air would be dense enough to feel like water around your body. Sound would travel slowly but clearly, vibrations passing through the fluid medium in deep, resonant waves that would feel as much as be heard. A single drop of the ocean would contain more pressure than the deepest point of Earth's Mariana Trench. Yet to native life forms, it would feel natural, balanced, serene, simply normal. Light would fade quickly with depth. A few hundred meters down, the world would turn red-black, illuminated only by faint chemical luminescence. Life's own answer to perpetual darkness. Perhaps tiny organisms drift there, glowing softly, exchanging heat and light as their primary language of communication. Perhaps immense, slow creatures glide through the warm abyss, sensing one another through electric fields and pressure waves rather than sight. Every breath of that ocean would be chemistry in constant motion. Methane rising from the depths would mix with carbon dioxide from above, producing new compounds that feed microscopic life. Hydrogen dissolved in the water would serve as both protective shield and metabolic fuel. On Earth, such chemistry builds cells and powers ecosystems. Here, it might build something stranger, more exotic, biology that doesn't rely on oxygen at all, that breathes hydrogen and exhales entirely different compounds. And yet, in many fundamental ways, it would still feel familiar to a trained biologist. Wherever we find life in the universe, we find balance, energy flowing in cycles, waste becoming food for other organisms, stability maintained through constant change. That is exactly what Webb has observed in the ratios of gases high above the planet's clouds, a living system regulating itself. In the mid-layers of the atmosphere, temperatures and pressures resemble those near Earth's surface. If any part of K2-18b could potentially host organisms similar to ours, it would be there, suspended in the air like plankton drifting in an invisible sea. Tiny microbial colonies might drift with the atmospheric currents, feeding on trace chemicals, absorbing what little light penetrates from the red sun. Each one would be a speck of life carried by the winds, rising and falling through a planet-wide ocean of air. We already know such aerial worlds can exist theoretically. In the clouds of Venus, scientists have found patterns of atmospheric chemistry that hint at microbes floating high above the hellish surface. K2-18b's atmosphere is far gentler and more stable. No acid storms, no suffocating heat, making it an even better candidate for aerial life floating in perpetual suspension. If the oceans below are the planet's heart, pumping and circulating, its atmosphere is the breath. Every molecule of methane or dimethyl sulfide that escapes the sea becomes a message drifting up into starlight. Those molecules crossed impossible distances of space and touched Webb's golden mirrors, carrying with them the unmistakable rhythm of metabolism, the pulse of an alien biosphere operating according to its own rules. The beauty of this discovery is that we can read that molecular message without ever leaving home. We can sit on a quiet world, orbiting our own star, and through light alone, reconstruct another world's climate, chemistry, and perhaps its biology. From the tiniest distortions in a beam of infrared radiation, we can determine whether another ocean ripples with life, whether another sky holds the promise of rain. And rain it surely does. Water vapor in K2-18b's atmosphere forms massive cloud systems that rise and fall in slow convection patterns. As they cool at higher altitudes, they release precipitation that falls not as individual drops, but as sheets thick as mist, gliding through the dense air until they vanish into deeper layers. There the pressure is so extreme that the rain may transform into liquid metal or crystalline ice before finally sinking into the ocean below. Every state of water, vapor, liquid, and solid could exist simultaneously, stacked in atmospheric layers like pages of a cosmic story. That hydrological cycle, evaporation, condensation, rainfall, is the same fundamental one that shaped Earth's weather patterns and nourished its life. It's a reminder that even across light years of separation, the language of nature follows universal grammar. Chemistry follows the same rules everywhere. The deeper scientists look, the clearer it becomes that K2-18b is not just theoretically habitable, but dynamically active in practice. The planet breathes, it recycles, it changes continuously. Each new observation reveals motion, feedback, adaptation, the hallmarks of a living system rather than a dead one. Somewhere below the clouds, in the pressurized warmth of those alien seas, evolution may have already taken remarkable forms. Simple cells could have merged into colonies. Colonies could have learned to sense their environment, to move purposefully, to think in whatever way alien intelligence might manifest. All at a pace measured not in millions of years, but in billions, the generous timescale provided by a star that burns forever. We will likely never see them directly. Not yet, not with current technology. But the air they exhale, the molecules they release, have already reached us across the void. Tiny signatures of existence carried across space on beams of light. They are proof that we're no longer just passive observers of the cosmos, but active participants in its oldest conversation, the exchange between light and life. As the James Webb Telescope continues to gaze at this world with unwavering attention, every photon it captures brings us incrementally closer to understanding the unseen. The next step in this investigation will be to map the layers of that atmosphere in even finer detail, to measure how the light shifts with time, how the winds move in circulation patterns, how the chemistry evolves from year to year across multiple observational seasons. For now, though, it is sufficient to know this fundamental truth. Somewhere beneath a crimson sun, beneath clouds that shimmer like silk and oceans that seemingly never end, there exists balance, a living equilibrium between heat and cold, air and sea, star and planet. It is a balance so perfect it almost feels intentional, not designed by intelligence, but inevitable, as though the universe itself seeks life wherever physical conditions permit. And on K2-18b, the cosmos may have found one of its most enduring homes. A world breathing softly in the light of a red star, a world whose oceans remember the first warmth of creation, and whose sky carries the quiet, steady pulse of life that may have been beating for billions of years. For centuries, humanity has looked up at the stars and perceived only silence and emptiness. We projected our loneliness onto the cosmos, and then came K2-18b. Not the twin of Earth we expected to find, but something more mysterious and profound. More an ocean world shrouded in hydrogen, orbiting a red sun far from anything we've ever called home or familiar. Its discovery didn't just expand the boundaries of astronomy, it expanded the boundaries of imagination itself. Because for the first time in recorded history, we're not just wondering philosophically if life exists elsewhere, we're seeing the tangible signs that it does. When Webb's golden mirrors revealed the faint traces of dimethyl sulfide in that distant atmosphere, it was more than data points on a graph. It was a tremor in the human story. In a few lines of spectral analysis, the silence of the universe cracked open, not with sound, but with evidence. That single molecule bridged an impossible chasm between worlds, separated by 120 light years. It said quietly but unmistakably, "You are not alone in the universe." The meaning of that cannot be measured in statistical percentages or confidence levels. It reaches deeper than science, into philosophy, art, belief systems, and fundamental human identity. It forces us to see life not as an exception or miracle, but as a principle woven into the fabric of reality. For generations, we thought existence was rare, that biology was a cosmic accident born of impossibly perfect conditions. But Earth has never been the only stage where the laws of chemistry and physics play out. They've been performing across the galaxy for billions of years, everywhere matter finds the delicate balance between energy and order. We have already seen the hints of life's versatility here on Earth. Microbes thriving in nuclear waste, bacteria sleeping for millennia beneath Antarctic ice, creatures living kilometers under the ocean, feeding not on sunlight, but on the geothermal heat of the Earth itself. Life, it seems, does not wait patiently for comfortable conditions. It thrives in defiance of comfort and ease. And now, 120 light years away, a world breathes under a red sun, proof that existence is not fragile or limited. It is robust and adaptable. If K2-18b genuinely hosts life, it reshapes everything we thought we knew about biology. Because red dwarfs, like its parent star, are the most common type of sun in the Milky Way galaxy. For every star like our sun, there are thousands like it. Smaller, older, steadier, more patient. If even a small fraction of them hold planets like K2-18b, then the galaxy is not silent and empty. It is teeming with possibilities. Billions of worlds, billions of potential beginnings, billions of ongoing stories we've never heard. The implications stretch far beyond astronomy and astrophysics. They reach into the very equation that tries to measure our cosmic solitude, the famous Drake equation. For decades, it was a thought experiment, a fragile attempt to guess how many civilizations might exist in our galaxy. Now, one of its most uncertain variables, the likelihood of life emerging, has shifted from a question mark to a near certainty. Life, it seems, doesn't wait patiently for Earth-like conditions. It emerges wherever chemistry and time are given sufficient room to work their magic. If biology can breathe hydrogen, if oceans can sustain life beneath red suns, then the definition of habitable becomes almost universal rather than restrictive. It changes fundamentally how we see ourselves in the cosmic story. For most of human history, our narratives put us at the center, chosen, unique, surrounded by divine emptiness. Then came Copernicus, who moved the Earth from the center of creation. Then Darwin, who placed humanity within nature rather than above it. And now Webb, which has moved life itself from the realm of miracle to the rhythm of physics and chemistry. We are not an exception to natural law. We are an expression of it. One verse in a song that began long before us and will continue long after we're gone. And yet this realization does not diminish us or make us insignificant. It connects us to something larger. It means that the atoms in our bodies, forged in dying stars, may also breathe and think elsewhere in the cosmos. The same chemistry that flows through our blood may flow through alien oceans. The same physics that ignited our sun lights a trillion others across the universe. The James Webb Space Telescope has become our new sense organ. Not eyes or ears in the traditional sense, but something deeper and more profound. A way to perceive life through light itself. Each photon it captures is a syllable in the language of existence, traveling for over a century to reach us with its message. And it's not alone in its search. Other observatories, the Nancy Grace Roman Telescope, the proposed Ariel mission, LUVOIR, and future ground-based giants, are already being built to continue and expand the hunt. Soon we'll be able to analyze not just one world, but hundreds, perhaps thousands. If even a handful show the same chemical imbalance, the same whispers of metabolic activity, then life is not a miracle or accident. It's a pattern woven into the cosmos. Imagine the future night when we realize with certainty that every constellation hides living worlds. Each faint star we see, a sun with oceans, clouds, and chemistry of its own. Some of those worlds may be primitive, just beginning their evolutionary journey. Others could be ancient beyond comprehension, their civilizations having risen and fallen before the first humans carved stone tools. But even if we never meet them, never make contact, their existence fundamentally changes the meaning of ours. Because for the first time, we know that life on other worlds is much more accessible to detection than we thought. For philosophy and faith alike, this discovery reframes everything we believed. If life fills the galaxy, then creation itself is not selective or rare. It is abundant. The sacred becomes not something that happened once in one special place, but something that happens everywhere matter organizes itself according to natural law. The miracle is not that life exists here on Earth, but that the universe allows it everywhere the conditions align. And yet, this revelation carries a mirror that reflects back on us. We have found proof that life may thrive under alien skies, while ours, under a bright yellow sun, trembles under the weight of our own making. K2-18b is balanced, steady, enduring. Earth, by comparison, feels restless and fragile. The universe has shown us what sustainability looks like, not as a political ideal, but as a natural law governing planetary systems. Perhaps this is the real lesson of K2-18b for our civilization. That survival is not about domination or conquest, but about equilibrium. Life lasts longest not when it conquers its environment, but when it cooperates with it. When historians of the future look back on this era, they may call this the moment when astronomy became biology, when we stopped merely studying light and started studying life through it. Webb's golden mirrors, hanging in the void a million miles away, have become bridges linking our small blue world to something vast and enduring. Because even now, as Webb listens to the whispers from K2-18b, our own signals are moving outward into space. Radio waves, television broadcasts, the digital heartbeat of our civilization. They're expanding through space at the speed of light, crossing the distance to K2-18b and beyond. Somewhere, if that world truly breathes with life, our signals may already have arrived. And perhaps on its crimson shores, beneath those copper skies, something alive has paused, sensing a faint pattern, a rhythm in the cosmic static, a sign that it too is not alone in the universe. If that moment ever comes, if two worlds separated by 120 light years recognize each other's presence, it might be the greatest conversation in history. Not in language, not in sound, but in light and electromagnetic radiation. Until then, what Webb has shown us is absolutely enough. Enough to know that the universe is not silent, but full of hidden songs we're only beginning to hear. Enough to know that life is not fragile but inevitable given the right conditions. Enough to remind us that every molecule of air we breathe, every drop of ocean, every breath we take, connects us to something older and greater than ourselves. And as Webb continues to gaze into the dark, collecting the faintest whispers of alien seas and skies, we begin to understand the truth that has waited so long for us to hear it. The cosmos is alive. The universe breathes. And we are part of that breath. The discovery on K2-18b is not an ending, it's a beginning. The first measured hint that life may not be confined to Earth or even to Earth-like worlds. From this moment forward, the fundamental question changes. We no longer ask if life exists elsewhere, but how many forms it might take and how far it extends across the galaxy. Science is already shifting in response. For the first time, astronomy, chemistry, and biology are merging into one unified discipline, a systematic search for patterns that define life across the galaxy. Researchers are calling it comparative astrobiology, the study of atmospheres, climates, and chemistry as connected systems. No longer isolated dots of light, planets are becoming data points in a living map of the cosmos. On Earth, new laboratories are recreating the conditions of alien worlds in controlled environments. Pressurized chambers mimic the dense hydrogen skies of sub-Neptune planets, testing how carbon, nitrogen, and water behave under temperatures and pressures unknown to Earth's surface. Some experiments run for months, watching molecules evolve into complex organics that may one day help explain how biology begins anywhere in the universe. Others focus on the chemistry of equilibrium, searching for the critical point where pure physics gives way to metabolism. The goal is to build a comprehensive library of biosignatures, a catalog of what living atmospheres truly look like, no matter their exotic composition, whether they're based on oxygen like Earth or something completely different. Artificial intelligence is quietly becoming the interpreter of this new astronomy. Machine learning systems trained on Webb's data can recognize molecular patterns invisible to the human eye. Faint combinations of gases, seasonal fluctuations, tiny variations in brightness that might indicate weather patterns, or even the growth cycles of alien biology. What once required months of painstaking manual analysis now happens in minutes. Each new dataset refines the algorithms further, teaching machines to detect the smallest chemical heartbeat in the vast noise of space. These AI systems are learning to see life not as we imagine it, but as it actually exists, in all its possible forms. Around Earth, a new generation of telescopes is preparing to take the next revolutionary steps. The Nancy Grace Roman Space Telescope, launching later this decade, will identify thousands of exoplanets and provide the first large-scale census of their types, sizes, and orbits. Europe's proposed aerial mission will follow, studying the atmospheres of thousands of them in unprecedented detail. On the ground, the extremely large telescope in Chile will combine adaptive optics and massive mirrors to measure the isotopic makeup of distant skies. Subtle ratios that can reveal whether a planet's gases come from geology or biology. Together, these observatories will form an interconnected network, a planetary survey system turning distant points of light into measurable, comparable worlds. The next leap will not be in data quantity, but in vision quality. Engineers are developing new optical technologies, advanced coronagraphs, and deployable star shades, capable of blocking a star's light so completely that the dim reflection of its planet becomes directly visible. A single pixel of that reflected light can reveal color, cloud cover, and rotation. With enough pixels, we might one day see continents or oceans glinting under an alien sun. Concepts like NASA's Habitable Exoplanet Observatory and the LUVOIR mission could make that possible within decades. These telescopes would not only detect life's chemistry, but observe its climate in motion, seeing seasons change, storms develop, and the slow rhythm of alien weather. Farther into the future, another vision takes shape that seems like science fiction, but is based on real physics, using the sun itself as a natural telescope. At a point more than 550 times farther from the sun than Earth, gravity bends light from distant stars into focus, creating what physicists call the solar gravitational lens. A small probe sent to that distance could use this effect to magnify a planet 1 billion times, resolving details as fine as mountain ranges or river systems. Reaching that distance would take decades of travel, but the technology is within reach of 21st century engineering. We know how to do it, we just need to commit to doing it. While telescopes study from afar, propulsion research looks ahead to the next frontier. Not just seeing other worlds, but physically reaching them. Concepts like Breakthrough Starshot propose fleets of laser-driven nanocraft traveling at 1/5 the speed of light. Their first targets will be nearby stars, such as Alpha Centauri, just 4 light-years away. But the same methods could eventually send microprobes to worlds like K2-18b. Closer to home, new propulsion systems are being developed and tested. Fusion drives, advanced ion engines, solar sails, each experiment in deep space navigation. Each test of autonomous control brings the technology of interstellar flight closer to practical reality. We are laying the groundwork for a future where humanity doesn't just observe distant worlds, but visits them. Yet the future of this discovery is not only about covering distance. It's also about understanding what it means philosophically and scientifically. As more planets reveal traces of chemistry that suggest life, scientists will begin to study not individual examples, but the statistics of existence across the galaxy. What does life prefer? Red stars or yellow ones? Deep oceans or shallow seas? Isolation or complexity? By the middle of this century, the study of life beyond Earth may no longer be a matter of rare finds, but of pattern recognition. Biology seen at a galactic scale. Taxonomy of alien life forms. This knowledge will not remain confined to astronomy. The same models used to understand other worlds can help us preserve our own. Studying atmospheric balance elsewhere sharpens our grasp of climate feedback here. How gases stabilize temperature, how oceans regulate heat, how fragile equilibrium can be. In learning how other planets maintain life, we may learn how to keep ours alive and sustainable. The implications extend further still. If we confirm life beyond Earth, even simple microbial life, it will redefine the ethical landscape of space exploration. The Outer Space Treaty of 1967 was written before such discoveries were possible. It governs territory and resources, not biology. New policies will need to protect alien ecosystems from contamination and exploitation, ensuring that contact means cooperation, not consumption. For the first time, space law may have to recognize the rights of life itself, however small or unfamiliar it may be. These are not abstract philosophical questions, but practical concerns that this generation will need to address. Beyond law and science, this search will reshape how human civilization sees itself fundamentally. For centuries, humanity has imagined the cosmos as a stage for human progress, a vast emptiness waiting to be explored and conquered. But as evidence grows that life exists elsewhere, that narrative changes profoundly. The universe becomes not a backdrop, but a community, a network of living worlds, each shaped by the same fundamental forces that shaped us. Our purpose may shift from conquest to connection, from expansion to preservation, from taking to understanding. Children born in the coming decades will grow up knowing that the night sky is not silent or dead. Every star they see could host oceans, atmospheres, and the slow rhythm of biology. Their maps of the cosmos will not end at the solar system, but extend naturally into the living galaxy. The question that defined generations, are we alone? Will fade into history, replaced by a new one. How do we fit within this greater web of life? For now, the work continues quietly, but purposefully. Each new observation adds a line to the story. Each new mission extends our reach. The data will accumulate until patterns appear that no one can deny or dismiss. And somewhere beyond those numbers, in the faint glow of red stars and distant oceans, we will finally see ourselves not as observers, but as participants in the same universal process. K2-18b was the first to whisper its secret. Others will follow. Each will remind us that life is not a singular miracle, but a recurring theme in the language of the cosmos. The telescopes we build next will not just look deeper into space. They will listen better, tuned to the faint harmonies of living chemistry across space and time. The future of discovery will not be measured in miles or even in light years, but in understanding, in how deeply we grasp the continuity between Earth and everything beyond it. And when the next signal comes, when another world joins the growing list of the living, we will recognize it instantly. Because we will have learned to read the signs, not as distant wonders, but as reflections of a shared origin. The search will never truly end. Each answer will open another horizon, each discovery another question. But this is what exploration fundamentally means, not reaching the end of the unknown, but continually expanding what it includes. And in that expansion, we begin to glimpse the real future. A civilization that sees itself not as the center of the universe, but as part of its living edge. In the end, discovery often feels less like revelation and more like recognition, a distant echo of something we already knew deep down. For centuries, we looked into the night sky and wondered who might be out there. Looking back, now we look and realize they were always there. We just hadn't learned how to listen properly. The light from K2-18b began its journey before any of us were born. It crossed the gulf of interstellar space while humanity was still learning to leave the ground, carrying within it the faint trace of air, water, and breath. When it finally reached us, it changed what it means to be human in the cosmos. We once believed the universe was silent and empty, an expanse to be conquered or explained through equations. But Webb showed us that silence can be deceptive. The universe is not mute. It speaks in chemistry, in the shifting ratios of gas and light, in patterns that whisper of balance and renewal. Life, it turns out, is not an anomaly or accident. It is a natural way for the cosmos to know itself. That realization reshapes everything about our place in existence. It tells us that the boundary between us and them, between Earth and elsewhere, is thinner than we imagined. The same processes that gave rise to plankton in our oceans may be at work beneath a red sun in Leo. The same laws that shape the air we breathe shape the clouds above alien seas. For the first time, our technology has reached a kind of empathy, an ability to sense the existence of something living without ever touching it. We are learning to understand life, not by seeing it move or grow, but by hearing its rhythm in the light of distant stars. There will be more discoveries, more signals, some clear, some uncertain. Each will remind us that we are part of a much wider story. A story not of isolation, but of connection. And each time a new world reveals its chemistry, it will feel a little less foreign and a little more like home. One day, centuries from now, explorers will stand on the shores of other worlds. They will see skies colored by unfamiliar suns, oceans that never knew our moon, mountains that rose without our gravity. But in those landscapes, they will find something familiar, the unmistakable logic of life adapting to survive. And when they look back toward the faint blue point of Earth, they will understand what Webb began, that the search for life was never about finding others to prove we're special. It was about understanding ourselves. Because in every spectrum, every equation, every photon that crosses the void, there is a shared truth. Life is not fragile or rare. It is persistent. It is creative. It is the universe's most eloquent form of continuity. The first breath on K2-18b, the first molecule that learned to replicate under a red sun, may have been the echo of the same principle that shaped us. Different chemistry, same fundamental idea. Survival, adaptation, awareness. When that light reached Webb's golden mirrors, it completed a circle billions of years in the making. the cosmos observing itself through the eyes of one of its creations. That is what makes this moment more than discovery. It is a reunion. The stars are no longer distant or alien. They are familiar, not because we have gone to them, but because we now know they live. And so the search will continue with renewed purpose. Not driven by loneliness, but by kinship. Every telescope, every mission, every experiment will add another note to the same quiet melody that connects all living things across the universe. The universe was never empty. It was waiting. Waiting for something that could see and wonder and finally understand. The cosmos breathes, and we are learning to hear that breath in the whisper of distant light. If you enjoyed this exploration of cosmic discovery, don't forget to leave a like and subscribe. It makes a tremendous difference and helps the channel continue bringing you these stories written across the stars.